All right, so let's talk about vehicle testing. We'll talk first about the 1/3 scale aircraft. Here you can see in this photograph on the right of the assembled aircraft, it had a gross takeoff weight of 22 pounds. And the first step of the testing was gimbal stand testing. This was to basically evaluate the system, figure out how it's going to respond to inputs and stuff. And so here you can see the rotor system. It's mounted to the gimbal with a spherical joint and some counterweights to bring the CG to that spherical joint. And we had it mounted in a 3x4 foot wind tunnel for forward flight testing. All right, so here's a video of the rotor head testing in the wind tunnel. Pilot is providing, roll inputs, yaw inputs, pitch inputs, and there were no unexpected dynamics. So that was a really good result of this testing. Okay, so the next phase of testing was indoor tether testing for the subscale. This was to tune the flight controller and trim the rotors and stuff, and it performed well, and it was demonstrated stable flight. So that was a good result from that. Yep, so here is some indoor free flight testing. This was the next phase of the testing, and it demonstrated all the flight capabilities that we were expecting. It performed very well, and we actually used this video documentation as part of our phase 2 submission, proof of aircraft operation. So the fourth phase of testing was outdoor free flight testing. Yeah, so this was the fourth phase of testing. This was to basically demonstrate forward flight capability, demonstrate maneuverability and controllability in high-speed forward flight. And we were pretty happy with the performance of the aircraft. That rigid rotor system really turned out to have a lot of control authority, and of course in the hands of an experienced RC pilot that helped a lot. Okay, and then we also did do some sound pressure level measurements of our system in comparison with a thrust matched quad rotor. And let me show that here in this video, where we'll just listen in and hear the difference between the quad rotor in comparison to our system. And so here you can clearly tell that there's a marked difference between the two. And then here's some of the results from that testing, sound pressure level versus frequency for the two systems. And our system was about 18 dB quieter than that of the quad rotor. We also looked at efficiency as well. We experimentally measured the power and thrust for the two systems and found that the quad rotor required nearly 55% more power. So not only was our system quieter, but it was also a lot more efficient as well. All right, so let's talk about testing the full-scale vehicle. So here is a photograph of the assembled aircraft, weighed about 550 pounds, empty weight, and could carry a payload of about 200 pounds. So the first phase of testing, as with the subscale, was gimbal stand testing. All right, so here we're doing the gimbal testing with the full-scale aircraft, and pilot is just giving some inputs. And as with the subscale, it behaved very well, very favorably. There was no unexpected dynamics, so we were pretty happy with that and gave us confidence to do tether testing. And so here we are doing some indoor tether testing with the full-scale aircraft. The pilot's providing some different inputs, and it responded favorably. And I'll note here the tethers are just for safety. They're not actually affecting the dynamics of the vehicle at all. And then from that, we collected some of the flight test data. This is the pitch and roll desired and measured rates. And the reason why these are important is because our flight controller was tuned by using these rates and angles. And we got pretty good agreement between the two of them, demonstrating that our flight controller is pretty well tuned. And there is a little bit more noise in the measured result, which is kind of expected for the rotary system. Now, during tethered indoor flight testing, we did do a hover endurance test, which lasted about 8 minutes. And here's some of the telemetry data from that. And we actually monitored this telemetry in real time and for all of the flight testing. So this helped us to basically evaluate the state of the aircraft at all times. Now, during indoor tether testing, we also did a payload test. And so we've loaded it up with 165 pounds of payload, and the aircraft lifted it very well. There were no issues, no unexpected dynamics, nothing really changed with the system. All right, and so the next phase of the testing was outdoor tether testing, and this basically allowed us to have an intermediate stage between indoor tethered and free flight outdoor. Another thing we did also was we measured the sound pressure level at 50 feet during this test. So let's play this here. So here we can see hovering at 50 feet, we're getting about 73 dBA or so, which is pretty remarkable for this size aircraft. In fact, as far as we know, this is the quietest aircraft in this weight category, the quietest rotorcraft in this weighted category that we know of. All right, and then the final phase of testing was outdoor free flight testing. And this, of course, was to demonstrate the forward flight capabilities of the system. All right, so here is the outdoor free flight testing of the full-scale aircraft, and it performed pretty well. It handled very smoothly. Here you can see the pilot just doing some back and forth laps over the tarmac. Unfortunately, it ended up crashing, so we weren't able to demonstrate it in the final fly-off, but we were pretty happy with the way it performed here. Okay, so with that, we'll summarize briefly. So Team Harmony, we designed and developed and flight tested both a subscale and a full-scale, ultra-quiet, coaxial helicopter personal air vehicle as part of this competition. We were, of course, phase 1 and phase 2 winners, and some of the key innovations in this project included developing ultra-quiet and efficient rotor systems, using rigid rotors with independent collective and cyclic control, implementing electronically coupled dual swash plates for mechanical simplicity, and then, of course, we developed a custom electric powertrain and custom transmission, ultra-quiet transmission, and then developed 11 kilowatt-hour custom battery pack. And the key thing here is that our team designed, built, and flight tested a full-scale aircraft in a mere 10 months. So this speaks to the dedication and commitment to our team. So some of the key takeaways, some of the lessons learned. So we demonstrated first that it is possible to significantly quiet rotors without losing efficiency. Specifically, we measured 73 dBA at 50 feet, which is pretty remarkable. And we were able to achieve this through tip speed reduction, planform shaping, and acoustically tailoring the blade design. Another thing we saw is that endurance really is still a serious limitation for eVTOL aircraft. We were able to meet the size and the noise constraints, most likely the speed constraint as well, but definitely not endurance. In fact, our longest hovering flight, as I mentioned, was only 8 minutes. That was from full charge to almost completely depleted, and that was with no payload. So this really just speaks to the low energy density of current battery technology. We were only about 133 watt-hours per kilogram at the pack level. Also, there is a need for reliable, lightweight aerospace grade COTS parts, specifically for eVTOL applications. We had numerous mechanical and electrical issues. Some of these were expected just as a process of developing the aircraft. But some of the COTS parts were pretty heavy. For example, the motor controller, some of them were unreliable, the first autopilot that we tried. And so these are some of the key results from this study. So the question is, what's next? Well, we are still pursuing the GoFly prize. There's no winners yet. It's still an ongoing competition. So if we can at any moment demonstrate that we have an aircraft, then that prize is up for grabs. Now, we did start a company, a small business, Harmony Aeronautics, as a result of some of the IP that we have developed. And this is specifically focused on ultra-quiet rotor technology in general application for eVTOL aircraft. And so Harmony Aeronautics, we won a phase 1 Air Force Agility Prime STTR grant. This was through the AFWorks program. And this was a 6-month, 150K feasibility study on developing these ultra-quiet rotors for eVTOL and UAMs. And so we were fortunate, we got an MOU signed, and we submitted a phase 2 proposal. And so we are currently awaiting those results. And they should be coming out here in a few minutes. We're biting our nails, just waiting for that result. But if we do get that, then we'll be full steam ahead on this endeavor. So I know that was long. I thank you so much for your attention. And if you have any questions, be more than happy to answer them.